Hello and welcome to Kennedy Space Center here in Florida for today's NASA Social program, taking you behind the scenes and getting an inside look at GOES-S. GOES-S is America's next weather satellite, launching tomorrow at 5:02 p.m. Eastern Time here from Kennedy Space Center. We will be taking you through a variety of different experts looking at different facets of this mission and asking all sorts of interesting questions. If you're following along online, you can ask your own questions online to us by tweeting using the hashtag AskGOES. That's AskGOES. We'll be having folks here in the room who have joined us from all over the country in sharing their questions around the different mission aspects. And we'll have experts joining us for the next hour. And so with that, from Kennedy Space Center, let's take it away with our first speaker here, the GOES-S System Program Director, Mr. Tim Walsh. Tim?
Good morning. I got to tell you, it doesn't get any better than the day before launch. Well, maybe launch day. So we're so excited about tomorrow. We are, I've worked on GOES-R for a number of years, probably too many, but about 10 years. And I started out as an engineer. And so when I came over from NASA as a contractor to NOAA, I knew that NOAA had a long program called GOES. But I mean, GOES started back in 1975. We launched GOES-1 back in 1975 in October. And we've been working with NASA nonstop to upgrade these satellites and to put them up there on a cadence that keeps us with knowledge of what's going on. I'm going to start a visual that kind of gives you a sense, if we could bring up the first video, that kind of gives you a sense of what our constellation looks like. We have two satellites looking at the Earth at all times. Right now we have GOES-East, which is GOES-16, and providing that incredible imagery that you've seen, both geostationary lightning mapper, our new imager, the advanced baseline imager. Phenomenal stuff. We actually had a hurricane season that was devastating on the ground, but it gave us a lot of incredible data to validate our new instruments. And so we were very thankful for that. Thankful to Mother Nature and others. But this will give you a sense of, from the east side, you see all of CONUS and all the way to the west coast of Africa. So when you're looking at tropical storms, you get a really good sense of what's coming. But really to complete the picture, we have two satellites that need to give us all the information. As you know, most of the weather doesn't originate in the east. It originates in the west. And so we need to have another piece of the puzzle is GOES-17, which will become, GOES-S will become 17 once we get on orbit about 14 days after launch. And so what we'll do is we'll use that data from the GOES-West satellite, which will extend all the way from almost New Zealand. We'll see all the way out there. We'll see Hawaii and Alaska. And so, so my role today is really to tell you about what our big picture looks like. One of the key things that I'm looking forward to with GOES-West is we're going to see parts of Alaska in ways that we've never seen before. And specifically, the high latitude parts of Alaska, from a geo perspective, remember, a geosatellite is over the equator. So we're looking at a very oblique angle when we look at Alaska. And it's hard if you don't have good spatial resolution to see what you can, to do weather and maybe fire tracking and other things. So we're going to see stuff that we've never seen before. I can tell you that for GOES-16, which is over 75 west longitude right now over the east coast, we can see elements in West Africa and even in Spain. I've seen some images of parts of Europe that we could never see using our old imager. So I'm very excited about it. But I do want to tell you that the NOAA fleet of satellites is more than 15 right now. We have LEOs with the low Earth orbiters that zip around the Earth every 90 minutes. And our GEOs, which orbit the Earth once every day, which 24-hour period, is unique in that you can always see the same spot of the Earth at all times. So if we can bring up the next graphic, it's very busy, but I want to give you a sense of what we do. We actually integrate the information from a number of different satellites, and the kind of cool thing about working for NOAA is that we integrate with a lot of other meteorological agencies. Like in the West, we have the Japanese Meteorological Agency, JMA. They actually use an imager that's very similar to ours. And then on the East, we actually have EUMETSAT, which is a number of nations that got together that have kind of the European version of NOAA. And that's really powerful because we basically stitch together all the data. And for a little later, you might hear a little bit about modeling. But when we pull all that data into our models, we use all of that information from all these satellites to look at all of our to kind of improve our weather forecast. So I'm really excited about what GOES-S will bring, and then GOES-17. And probably in 6 months from now, you'll start to see the imagery and really in your operational data. So with that, I'd love to take any questions. Anybody?
All right. So if people have questions online, you can get those questions using the hashtag AskNASA, and we'll have someone here in the room looking up those particular questions. And if you're here in the room, if you can raise your hand, we'll have a microphone come out to you. So first question is down front here.
So someone wants to know, for how long were you working on this project?
I actually came over in 2004. So we actually were creating the requirements. And that time, for us, it means usually working with the National Weather Service. Everyone knows the National Weather Service. So I was working, it's a unique program because we're actually at NASA Goddard in Greenbelt, Maryland. But we interact with our partners with the National Weather Service, creating those requirements. We started building the satellite. We actually had the contract for the satellite in 2009. And so it's a long time. So you develop all these 6 amazing new instruments, and you have to integrate them on a spacecraft. Then you integrate it to a launch vehicle. And that's where we are today. That's why there's a lot of excitement here.
All right. I saw another question. We'll go down front and then go in the back here.
So how fast does the data transfer between the satellite and Earth? So if you're monitoring an event, how fast does someone on Earth actually see the real-time data?
Actually, it's a great question because there's something called data latency, right? And so we get the data immediately, speed of light, and then we have to process it on the ground. And we do some pre-processing with that raw data so we actually send it back to the satellite to send to the whole Western Hemisphere. So we distribute our own products that way. And all that happens in a matter of seconds. And so different products have different latencies, and I won't get into the great detail, but we have 34 products. Some of them require predecessors to be created. So some have on the order of multiple seconds or tens of seconds. But to me, it's amazing that what you see on the web essentially is near real time. It's pretty cool.
Question in the back.
What is the, first, is GOES-S a carbon copy of GOES-R? Does it have the same equipment, or were there some upgrades between R and S? And what is the operational life expectancy of GOES-S?
Okay. First of all, I'll answer the second one first, which is we're 10 years on orbit mission operational. We actually have a 15-year lifetime on orbit. By that, we loaded with enough fuel to stay on orbit for 15 years. Having said that, the engineering was so good on the spacecraft that they kept the mass low, and so we basically topped the tank, so to speak. And so when we launch tomorrow, we'll have almost 19 years worth of fuel on board. Now, hopefully the instruments can last that long, but right now the instruments are designed to last for 10 years. And now, going to the first one, Pam Sullivan will follow me, and she's the creator of she's the flight project manager, so she can talk about specifics. But it is very much the same 6 instruments that we have on GOES-S, but we've made some tweaks, and that Pam will talk about, that primarily to address some of the things that we saw on orbit with GOES-16. But the ABI and the GLM are primarily identical.
All right, next question is down front here, and then we'll come over here.
GOES-R went into service last year, and we saw some fantastic results from it already. What I'm wondering is, did you learn anything from GOES-R that at the last minute you may have tried to incorporate into GOES-S?
Absolutely. In fact, and I'll mention a little bit, and then Pam, you can either correct me or fill me in afterwards. But there's a couple things that we saw with some of our non-nadir pointing or non-Earth pointing instruments. Like our magnetometer is something that's a very sensitive instrument that's looking at the geomagnetic field at the location of the spacecraft, and it's affected by other currents and other things going on the spacecraft. So you have to carefully accommodate that instrument. For GOES-16, we didn't see the performance of the magnetometer the way we'd like, so we're very excited about we think we tweaked a lot of things on GOES-S to fix that problem. The other thing is we added some extra shielding in a couple places where we saw some upsets, and added some more blanketing where we thought we had thermal issues and such things like that, but nothing major. It's primarily the same spacecraft.
All right, next question is down front here.
So with GOES-R, it took us a year to get the data operational. Is it going to be shorter now with GOES-S? I know you said in 6 months we'll start to see some of the images. Is it going to be shorter, the testing processes?
It's a good question because we do have a 6-month phase of testing. Actually, to give you the timeline, it takes us 2 weeks to get to the geo orbit. It takes us about a month after that to what we call outgas. We want contaminations to boil off the spacecraft. And then we take about 5 months after that to test all the spacecraft and the instruments. We did that for a year for the first one. That's the first of a kind. So we had to focus extra specially, and we had to validate all our products with our users. And we think that by the hurricane season this year, we'll be ready to go. And I will say that even though we went operational December 18th of last year, I have some National Weather Service friends in the audience. I know that the data was used almost immediately, so that was a really encouraging. Yeah, yeah. No, we'd love to see that. So.
Wonderful. Next question's in the middle here.
Not to get too far ahead of ourselves here, but we've heard a lot about the revolution in the science of forecasting that's come from GOES-R. What's next? Are the next spacecraft in the series essentially the same, or are you dreaming about what can happen in the future?
We are always dreaming. So I will tell you that it is a long time to bring this stuff to orbit, right? We have to balance the risk of doing something that we know will survive on orbit with the packaging and of course the cost. It's not cheap. So there are 2 other spacecraft after GOES 16 and then 17. TNU will be launched in summer of 2020 and summer or spring of 24. So that seems like a long time away. But that's to keep us so that we have always 2 satellites in orbit at any given time, and that's to bring us to the 2030s. Now, having said that, we're already starting the early discussions, talking to our users to say, what are those next generation requirements? But I just finished talking to somebody about our current instruments. We're really just unwrapping them. It's like Christmas Day, right? And so we're finding some things that we didn't know we'd expect to see. And I think there's some speakers coming up after me that could talk a little bit more about that. But I think we're going to be discovering new ways to use our current instruments for at least another decade. And like our geostationary lightning mapper, along with our imager, will give us some insights to storms that I don't think we ever anticipated, to be honest.
Next question's in the back here.
Between GOES-S, which will become 17 on orbit, and 16, are they meant to complement each other or to do their own independent missions on their own?
They are certainly to complement. In fact, I didn't really probably explain it too well, but when you saw that CONUS imagery, we actually have an overlapping region. So now we have what we can do is we can sync up the imagery profiles or sequences that we do on the satellites so that we'll have every 10 minutes a full disk image from both the East Coast and the West Coast satellite. We can stitch together and have really constant surveillance of the whole Western Hemisphere for every 10 minutes. And we can work with the Japanese on our left and our European friends on our right and maybe look at 2/3 of the Earth at any given time in the future. So yes, they're completely coordinated.
Next question, we'll go here, second row.
How long after it launches does it take for it to get set up and for it to start orbiting in its correct path and stuff like that?
Okay, well, the fun for me starts about 3.5 hours after launch tomorrow. That's when life begins, right? That's when we let go of the satellite, or launch vehicle lets go of us. And then about 3 hours, 47 minutes after launch, we deploy the array. We get power for the first time. And then life begins, right? We have about two weeks of maneuvers where we circularize the orbit. And then, as I mentioned, about a month of time where we boil off gases or boil off contaminants off our instruments. At that time, we're testing the spacecraft itself. And so about May-ish is when you'll start to see data coming off the satellite in a test form.
All right, next question's down front here. Oh. Sorry.
I'm pretty interested in delay-tolerant networking. So I was wondering if you guys see a lot, or high latency and redundancy when you have a lot of difficult weather forecasts and hurricanes and such. So do you see any communication problems when that comes up?
I'm not sure I'm going to answer your question properly, but there's some people after me that probably could as well. But as far as when we have severe storms, are you saying do we have additional times that does the latency increase, for instance? Well, no, our systems are designed, our ground system is something I haven't even talked about, but it's a behemoth. It's basically a supercomputing system that does everything from what we call command and control to data processing and data distribution. We've sized it for the largest volume we could anticipate. And then working with the Weather Service, we have requirements for this latency that we have to meet. And so we have margin on that so that we meet those latency requirements. I don't see personally an issue with that. But one thing that's interesting that you just reminded me of is we have our ground system that receives all this data is on Wallops Island, Virginia. And for those people that are in that area, it's basically I don't want to be quoted on this, but it's a sandbar. It's on the ocean, right? It's right off the ocean. And so for me, when I first came to NOAA, knowing that our primary receive station was so close to something that ironically could affect it, like a hurricane, one of the cool things about GOES-R is that we now have a backup site in West Virginia that's close enough that we can go away, but far enough away that meteorological events or other issues would not affect it. So we've kind of built in all the backups that we would need to keep that data flowing. So,
all right, next question down front here.
So I think a lot of people who may not be that familiar with the satellites and space and stuff might have a very basic question, like how big is this satellite that you're getting ready to put up in space? I mean, what is it relative to something that here on Earth?
You know, it's funny. I have to come up with a good story by tomorrow because, you know, people say like it's a pickup truck or something like that. I think AJ and Pam are coming after me. Actually, they touched the spacecraft, so they can describe it. But I will tell you, it's one thing that I always thought is neat, and I came from a orbital and attitude dynamics type background, but we utilize most of our mass, or at least 40% of our mass getting to orbit. So when we launch, we're at about 5,200 kilos. It's a good-sized spacecraft. Fully loaded with fuel. About half of the weight, half the mass roughly is fuel. When I say fuel, it's fuel and oxidizer. So we utilize a lot of that just for the first 14 days of the mission getting on orbit. Now the satellite itself, from the ring that attaches to the launch vehicle all the way to the top of the ABI, is between 20 and 25 feet. And it fits in a 5-meter fairing, so that gives you a sense of how wide it is too. If you look at that thing tomorrow, you'll see it's the big hammerhead on top of and I know we have a ULA representative coming up after me, can give you a sense of how big it is too. It's good size.
All right, we've got time for one last question here. So you've had your hand up for quite a while here. So.
Okay, so someone wants to know, what is the purpose of the satellite, and is there any astronauts going on this mission?
I get that a lot. I do. And I did ask for some NOAA astronauts as a result of one of those questions. No, but there's nobody that will fly on the satellite. But for NOAA, the mission that we do is operational in nature. So it's all about lives and property. So whether it's giving people evacuation notices for hurricanes, telling people about forest fires or whatever, it's a little different. When I used to work at NASA on more like one-of-a-kind scientific satellites, it was always hard to relate to my parents what I did. Now you work on GOES. Everybody knows GOES, which is cool. But it's really all about saving lives and property. Yep.
Wonderful then. Thank you very much, Tim, for joining us today. All right, now that we've talked a little bit about the kind of program here and what's launching tomorrow, we're going to dive into the spacecraft a little bit here. Coming up next is Pam Sullivan. She is the GOES-R flight director. And we also have AJ Sandora, who is from Lockheed Martin, who helped build this. So they're going to tell us all about the spacecraft.
Wow, I like that applause. That's great. Those are great. Hi, good morning. Let's see, as was said, my name's Pam Sullivan. I am the GOES-R series flight project manager, and I have responsibility to build all 4 of the GOES-R satellites. And of course, we're super excited by what we've seen with GOES-R over the past year. It was a really great year to be a weather satellite with all those hurricanes, and we even had a solar flare, the largest in a decade, that happened, and that doesn't get talked about a lot. But it's really been awesome to see the first of our babies in orbit and working, and just as excited to see the second one come up as well. And so in my title, the flight part of that title basically means I'm responsible for the parts of the mission that leave the ground. So that includes the spacecraft, the instruments, the cameras that it carries, and the launch vehicle. And so I have a responsibility to develop all of that flight hardware. And my job really starts with NOAA and the National Weather Service. And all of those forecasters, they really tell us what data they need to see. And so for GOES-R, they said, okay, those other satellites are great, but what I need now is, I still need to be able to look at the clouds and the weather, but I also want to look at volcanoes and ozone and carbon dioxide and fires, and I need to see all these different things. And they said I need improved ground resolution, and I need the data faster. And so, so I took those requirements, me and my team on the flight project, we take those requirements, we translate those into very specific technical requirements for what the hardware needs to do, and then we hold competitions, and then industry basically competes to build those instruments. We select who we think can do it the best, and then we translate that, and we help the industry partners basically do the design for the instruments, build them, put all the parts together, test them, and get them delivered to the spacecraft. We do the same on the spacecraft side. The very unique requirements that come to us, again, we translate what that means for the spacecraft. And I'll give you a couple examples on for the instrument side. With all those new observations that the Weather Service said that they wanted, we selected Harris Corporation to help us build our main camera, the Advanced Baseline Imager. And so we basically designed a camera that has 70 megapixels. It sees in 16 different spectral channels, which is 3 times as many as the old one. It has down to quarter-kilometer ground resolution, which is 4 times better than the old ones. And it can scan the entire full disk of the Earth in 5 minutes, which is 5 times faster than the old ones. So, so we use that. So we came up with that design based on those requirements, built that instrument with Harris. Another example, the forecaster said we have to see lightning. It's really important to see lightning because that tells us how storms are intensifying. It tells us where tornadoes might be coming. And we had never built an operational lightning mapper before, so that, again, was kind of really exciting to design that. And we worked, in this case, with Lockheed Martin to build our lightning mapper instrument, and we designed a camera that can take pictures 500 times a second, which is how fast you have to take it if you want to catch something as fast as lightning. And so, again, a brand new development with that. We built 4 other instruments, mostly solar and space weather instruments as well. And then we worked with Lockheed that we selected to build our spacecraft, and we said, hey, we're building all these great new instruments. Now your spacecraft has to do some really special stuff too. And so the primary thing that you can probably think of is it needs to point really, really stably. You know, it doesn't do a lot of good to make a super instrument, but then having it moving around because the satellite's moving around. And so we said, you know, you got to have star trackers and gyroscopes and accelerometers and all these things on board that can keep the satellite very, very stable. And so we've got a design right now that if you were a mile away and holding a nickel, the satellite could hold focus on that nickel from a mile away. So really super tight pointing. And the other thing that's really kind of unique on this satellite, the forecaster said, you can't ever stop taking data, which is perfectly understandable from a forecaster's perspective, but really, really hard on a satellite. You know, satellites almost always stop. They have to do some calibration. They have to use their thrusters and move around the sky to, you know, kind of keep the orbit. And for the most part, including on the previous generations, the satellite stopped taking data when those things were happening. But the forecaster said, nope, not in this case. And so we had to design in some features, including some really tiny thrusters so that we can still do the maneuvers, but when they happen, they're such small forces that the instruments really don't see them. And so that was kind of a unique development, an actual technology that we developed specifically for this mission. And so anyway, so my job, like I said, is to help develop all that, to help our industry team build that, to build our 6 instruments. And then when we have the instruments all checked out and we think they're working the way that we want, we hand them over to AJ's team, and he puts the satellite together. So.
Yeah, thanks, Pam. My name's AJ Sandor. I'm with Lockheed Martin. I'm based out of Littleton, Colorado, so close to Denver. That's where we assemble the spacecraft. I work for an organization called ATLO. That's assembly, test, and launch operations. So my team is responsible for putting it together, so assembly and integration. So everything that Pam just talked about, we take those instruments, we work with the instrument providers, we kind of collaborate, put everything together onto the spacecraft. Then we move on to test, so we'll test it. So we put it through thermal vac to simulate space and acoustic to simulate the launch atmosphere. So once we do that, we see the results and make adjustments if needed, and then from there we go to launch. So the team that I work with, my team, we're down here we shipped the beginning of December, and we've been here, a lot of us have been here since Thanksgiving time, so eagerly awaiting for tomorrow's operation. So, yeah. What other part of assembly and test is we also have, as Pam mentioned, the 4 different spacecraft. So we had GOES-R last year. Simultaneously, we're building GOES-S. And right now we're building GOES-T. So GOES-T is in assembly. I think we're installing our second to last box today, which is one of our flight power units. And then we have one additional box after that. And then we'll start getting into some of the bigger installations, the solar arrays, and some of our antennas. But all of the instruments are installed already to their current position. The GLM ABI to the top of the spacecraft, and then SUVI and Nexus to the solar array, and then SICE as well. So everything is installed. We're getting ready to do as I mentioned, acoustic testing. That acoustic environmental testing is scheduled for June, and then we go into thermal vac in September. So exciting year for us with the launch and with GOES-T and getting it ready for launch as well. So.
Wonderful then. If you're following along online, you can ask questions using the hashtag AskGoes. And so in the room, any questions for Pam or AJ? We'll start over here.
Although I have questions, I'm going to channel my mother right now, who just texted me with a bunch of really great questions.
Oh, no, not the moms.
She's so cute. So she has a few, and in particular, you talked about those tiny thrusters. So she says, what part of space does it occupy? Is it in a certain arc, or does it permanently suspend over the U.S., and does it move travel? So maybe you could say a little bit more about this, but I love the next question. Does it have radar, so if a piece of space junk was coming at it, would it move out of the way? I think that's a great one.
Sure. So we're in geostationary orbit, and what that means basically is we are moving around the Earth. We're actually going at about 3 kilometers a second. But it looks stationary because the Earth is rotating beneath us. So we're at a rate that just follows it all the way around. So it is moving, but it looks stationary. And there are specific assignments of where you're supposed to be in orbit. I think Tim mentioned, so our GOES-R satellite is now our GOES-East satellite. It's at 75 degrees west longitude. That's more or less the longitude of the East Coast. GOES-S, when it launches, will move over to the West Coast, 137 west. That's more or less the longitude of the West Coast. And so, as Tim used the word sentinel, I think that's a great term, because that's basically what we're doing, is keeping a watch out on both coasts. And as far as getting out of the way, yes, we don't have our own radar, but there's a network of it's actually military and some civilian sensors on the ground that are basically tracking man-made satellites that might get in our way, as well as asteroids and things like that. And they do that job for us and for every other satellite that's up there. But they basically say, hey, you could have a close call with this particular object, and it recommends, which way you should move to get out of the way. And we do that process of looking out all the time, and we definitely move when we have to. It hasn't happened yet on GOES-R, so space is pretty big, so it's kind of hard to run into something.
Wonderful. There's a question over here. Yeah. In the
back. No matter how big the resolution, a really good camera doesn't really work well if you're trying to get a picture of the ground, but there's clouds overhead. So I'm assuming that you're going to use the satellite a lot to take pictures of the ground during various weather phenomena. What kind of cameras and light spectrums do you have on the satellites to prepare for that?
Yeah, so our main camera, the Advanced Baseline Imager, sees in visible light, which, as you say, is blocked by clouds and stuff like that, but it also goes out into the infrared, so beyond what our eyes can see, out to about 13 microns is the longest, and it's got channels kind of along the way, but some of those channels can see through the clouds, and so that's one reason that we can do the forecasting at night. But the channels are very specifically selected by scientists for the phenomena that they want to look at. And in some cases, we have channels that are designed to see clouds, some that are designed to see low clouds, some designed to see mid clouds, some designed to see high clouds, so that they can get sort of a temperature and moisture profile from that. And then, like I said, they want to see volcanic ash. There's a specific channel that's best to see volcanic ash in. And for fires, We use another of our infrared channels. The 3.9 micron channel is really good for that. So it is very much tuned to the phenomena that the forecasters want to observe.
All right, we've got time for about 2 more questions here. So we'll go in the back over here.
Hey, Pam, you had mentioned the Sentinel function and also the imaging for lightning. Can you speak to the imaging for tsunami forecasting, particularly since the function in the West will connect with what data the Japanese are collecting?
Yeah, the pictures are not great for tsunami forecasting, but one thing that does do, we don't talk about it a lot, but it also is a communications relay, and so we've got very sensitive antennas on board that there's a network of actually tsunami monitors. They're little buoys sitting out at oceans, and they're designed, you know, when they see a big wave come by, they say, hey, I just saw this, and they send the signal up to GOES, and we relay that down to a network of folks that are actually looking for such things, and so they make sense of that data from that data that we relay for tsunamis.
All right, last question here is going to be down in the front, second row. Yep.
Sometimes we hear about space missions that have lots of instruments, like Cassini, where the ground teams have to argue about which instruments to use, because you can only use one at a time sometimes. Can GOES use all 6 at once, or do you have to pick which one based on what the weather's doing?
Oh, no. Forecasters were very clear. Got to use them all the time, on all the time. And so, yeah, there's not really any trade-off. They're all working all the time. So.
All right, wonderful then. Thank you very much, Pam and AJ, for telling us about the spacecraft. All right. Up next here, we're going to hear a little bit about the rocket and the launch that's going to be taking place tomorrow. We have with us Mick Waltman from NASA's Launch Services Program, and we have Gabriel Rodriguez Mina from United Launch Alliance. So take it away.
Thanks. So, good morning. I'm Mick Waltman, as he said, from Launch Services Program, and we're very happy to be partnering with ULA and my partner here, Gabe, and we're going to talk a little bit about the rocket and what's going on. I will tell you, just got back from rollout. If any of you didn't get to see that, that was so awesome. It was a beautiful day for that today. Rollout occurred on time, 10 a.m. ULA made that look so easy. Got the rocket to the pad, and GOES S is ready to go. So I do want to show you a quick video of the flow real quick, if I can bring that up. What you got here is the arrival at the Cape in January of the Atlas V first and second stage. These stages are built by ULA in their factory in Decatur, Alabama. Then they're transported to the Cape via the Mariner ship that you see there. Here we see the offload of the first stage of the Mariner. It's transported across Cape Canaveral Air Force Station to the Atlas Spaceflight Ops Center, or the ASOC, for pre-launch processing. In parallel with that, ULA processes the Centaur upper stage, transported to the Delta Operations Center, or the DOC, for pre-launch processing and integration. We call this the Off-Site Vertical Integration Assembly, or the OVI. Then you see the first stage booster is rolled to the Vertical Integration Facility, or the VIF, at Slick 41, where it's placed on the mobile launch platform. Then after that, we start the erection and mate sequence of the 4 solid rocket boosters, or SRBs. This is the next part of the Atlas 541 configuration. Then we transport the OVI from its facility at the dock down to the pad at the VIF there to get ready to mate. This includes the Centaur, the inner stage adapter, and the boat tail. And that completes up the rocket part. And then, of course, the most important part, GOES S, our spacecraft, is processed at Astrotech, transported across Kennedy Space Center out to the VIF in the early morning time frame, lifted up into there and made it to the rocket to complete buildup. And we're looking forward to ULA and NASA working together to give GOES S a great ride.
Hello, my name is Gabe Rodriguez, and I'm part of United Launch Alliance. My assignment is I'm a system test engineer, and pretty much I work all throughout rocket integration. Part of my job is to test the rocket, troubleshoot it, and some AVE airborne console. Now let's talk some rocket. This will be an Atlas V configuration for 541, meaning 5-meter payload fairing with a 4 rocket booster, standing tall and proud at 197 feet tall. Also, the rocket will be weighed with the GOES-R spacecraft at 1 million pounds. And also, it will create about 2.25 million pounds of thrust at the pad. Now let's watch this close video about our launch sequence.
The following profile details the important events of this mission using approximate times.
4, 3, 2, 1. And liftoff.
The Atlas V RD-180 main engine and 4 solid rocket boosters ignite to generate the 2.25 million pounds of thrust to lift the rocket away from the pad. Shortly after liftoff, Atlas begins its initial pitch, yaw, and roll maneuvers to attain the proper ascent profile and minimize aerodynamic loads. The Atlas V reaches Mach 1, the speed of sound, at 35 seconds. At 47 seconds, the vehicle experiences maximum dynamic pressure. All 4 solid rocket boosters, or SRBs, are jettisoned at 1 minute 50 seconds. 1 minute 40 seconds later, the payload fairing is jettisoned. Approaching booster engine cutoff, the Atlas V burns propellant at a rate of 1,856 pounds per second, traveling at over 13,340 miles per hour, and is located 83 miles in altitude and 267 miles downrange. Booster engine cutoff occurs 4 minutes 22 seconds after liftoff. 6 seconds later, the booster stage is jettisoned. The vehicle now weighs a little more than 5% of what it did at liftoff 4.5 minutes earlier. 10 seconds after booster separation, the first Centaur main engine start takes place. Cutoff of the Centaur main engine occurs just over 12 minutes after launch. The mission now enters a nearly 10.5-minute coast phase. At 22 minutes 38 seconds, the Centaur main engine is restarted. This burn will last 5.5 minutes. Following the second Centaur main engine cutoff at 28 minutes 9 seconds, the mission enters a 3-hour coast phase. Just over 3 hours 28 minutes after liftoff, the Centaur is started for a third and final burn. Approximately a minute and a half later, final cutoff of the Centaur main engine occurs. At 3 hours, 32 minutes, and 31 seconds, Centaur releases the GOES-S satellite for NOAA and NASA.
United Launch Alliance is proud of working with NASA and NOAA in delivering GOES-S to orbit. GOES-S plays a vital role in space forecasting, storm tracking, and weather research. Also, our first United Launch Alliance has launched every launch for GOES missions back since the 1975. Once again, we are proud to work with our partners and everybody in the industry that works throughout this whole integration process. And as well, the United Launch team is looking for a successful launch next Thursday.
Thanks, Gabe. Appreciate that. I do have a question for you guys. How many of you were here for GOES-R? Okay, so you heard from Pam and them say the GOES-R project, the GOES-R series, right? And today we have tomorrow the GOES-S satellite. So that's just the next in the GOES-R product. So sometimes you'll hear Gabe and I refer to GOES-R project or GOES-S. I did have a question for Gabe because I think this is his first time in front of you guys. He did a great job, didn't he? Yeah. Right? Yeah. So Gabe, I want to know if it's the same thing for you as it is for me. You guys, you saw in the video, 28 minutes, we get to MECO 2. A lot of people go home. A lot of you go home. We still have to sit console for 3 hours. And I think for me, that last 1 minute burn is probably the most exciting. How about you?
So definitely liftoff, it's one of the most exciting times. Once you see the rocket fly away, it's just beautiful. And then after that, we stay tuned throughout MECO 1 and MECO 2. And then after that, we have our briefing. Pretty much we told the team how the rocket did, how it's performing, and if everything was expected.
Yes. And as Pam said, for Gabe, myself, and the NASA ULA launch teams, you know, this all culminates in launch tomorrow. But we've been working with ULA for the last, from a launch vehicle perspective, the last 4 years. And NOAA and NASA have been working with the GOES spacecraft for quite a long time. So this is a culmination of a lot of work between the partnership of ULA and NASA.
Wonderful. Then with that, we'll take a few questions from here in the audience. And so we'll start right over here.
What sort of adjustments are made to deal with different payloads? Is there kind of a one-size-fits-all fairing, or do you do very specific engineering for each different satellite?
So definitely every rocket has its own integration process, and all of them have different requirements. For this specific vehicle, we have a 5-meter payload fairing, and it all depends on the customer, what are their requirements and specifications.
Yes, I will follow up with that is the configurations that Gabe talked about, the 541. One of the jobs in LSP is to integrate that vehicle with the spacecraft. And as Gabe pointed out, they've launched every GOES mission on a ULA variant since 1975. GOES L, which was launched in 2000, became GOES West back in the day before it was decommissioned, which GOES S will now become. And it was launched on an Atlas 2A, which was a different variant. And again, because of the weight of the spacecraft and the requirements for orbit, we matched that vehicle up. And then today we matched the 541 because the GOES S is a little heavier. I think it's like 2,900 kilograms. So, you know, we have those 4 boosters for extra boost and then the 5-meter fairing to give it enough room for launch.
All right, next question's over here.
How many things need to go right in order for the rocket to successfully launch?
Everything.
Is there a number? I feel like there's got to be a wild number you guys got.
Everything.
So it's a long process, and I would say there's a lot of teamwork play along behind the scene. So GOES S is being, actually our vehicle is being processed since 2012. So there is a long list of things that we do to make sure that everything is on track. Now, there isn't such a number that we could say all of these things need to go right, but we do have requirements that we follow, and to make sure that those requirements are met and make sure that all of those avionics boxes are performing good, we do have test requirements that allow us to know that.
There's no real number. I joke when I say everything, but he's absolutely right. When ULA works with their sub-vendors, as you saw in the flow video, you have the solid rocket motor, you have the booster buildup. They build those vehicles in Decatur, Alabama, and they start from scratch. Raw material comes into the Decatur facility as stainless steel. They roll it, they mill it, and then they build up the RP1 tank. They build up the LOX tank. They weld those together. That becomes what we call the first stage. They do the same thing for second stage, so a lot of things come together. It's a lot of teamwork across the nation to bring a rocket to this like this together, plus the satellite. So
next question's down front, and then we'll come over here.
Allie, age 7 from Chicago, was wondering what would happen if something went wrong once it's in space. So what sort of backup systems do you have, or cameras?
On the launch vehicle or the satellite?
On the actual satellite. So once it's in space, what happens if something breaks?
That's a good question. Pam would have been a really good one to ask that question to, but what I will tell, but that's okay. But what I will tell you, based on our experience over the number of years that we've launched these things, is the satellite teams have a lot of contingencies built in and things on their vehicle that they monitor. Their ground team monitors that stuff and looks for stuff that works. I mentioned earlier GOES L, which was decommissioned in 2011. When they went to decommissioning, they were looking at different things that were starting to shut down, right? So they monitor those, and they have fixes and ways to bypass some of their systems and work to try to maintain that. Each satellite is designed for a specific time on orbit, and so they try to maximize that time. So,
wonderful. The next question's over here.
As you're designing and building and testing the boosters, what does that look like, and how many times do you have to go back and redesign?
So simple answer: every time we need to. We don't let the rocket go until it's absolutely ready, and we make sure of that. And it goes through a whole process. You know, like we come in and we board the tanks together, and our partners in the industry help us with that and bring all the parts together to Decatur, Alabama. And in there we assemble it, and then we come in and we deliver it to the launch site.
Atlas V, the configuration we're flying today, is a heritage. It's the Atlas whole family has built itself up from Atlas H's to 1s to 2 to 2A to 3s to now what we fly today, the Atlas V. It's an evolved vehicle. ULA has over the years continued to make design improvements and enhancements to the vehicle. So as Gabe said, it happens all the way up to launch day. Just in case you're wondering, the teams are actually working on stuff right now, looking, reanalyzing, just double-checking things. So it happens all the way up to rollout and launch just to make sure that we have the perfect vehicle ready to deliver the spacecraft.
Got time for one last question down front here.
Can you ballpark how many people and teams it takes to make a satellite in a day like tomorrow happen?
So from the spacecraft team, I'd have to let Pam and them answer that, but I could imagine it's a pretty large team, similar to the partnership with ULA and NASA. I can speak to the NASA side, and I'll let Gabe speak to the ULA side. But we partner with ULA on these launches, and from our NASA side, we have an engineering team of about 50 to 60 people. Along with our analysts who do a lot of dynamic environmental vibe shock work. There's probably about 100 people on the NASA side to make a launch like this happen. And again, this is an exciting year for us in LSP. It's our 20th anniversary here at Kennedy. And we've got 6 launches on 6 launch vehicle configurations in the next 6 months. And ULA GOES S is our first one. And then we have 2 more with ULA this year, so 3 of our 6 this year with ULA, including our last launch in September, which is ISAT-2, which is the last Delta II ever produced. So it's a huge thing for both NASA and ULA that we're closing out that product line, which has been an amazing workhorse for a lot of notable missions over the year, including Mars, Jupiter, Sun, all that. So. From the ULA side?
So I do want to say this. We are a family, and it takes about 3,000 people, which is our current ULA employment, for us to be able to make this happen. Now, on launch day, it's about, in LCC, it takes about 30 or 40 people to launch, but you cannot look at that. It's every person matters, every person plays a part, and every person is important throughout the whole integration and throughout the whole process.
Yeah, I did want to really quickly go back to the 7-year-old who asked the question. That is actually Gabe hit on something that's very important in this business, is we are a family. No matter who you work for, it is teamwork. It takes everybody, down to the business folks, down to the janitor, down to our news crew, down to our PR people. It takes everybody to make this happen and get people excited about space. And that's what we love. Hopefully we've shown that to you. We're passionate about our job. I know we could sit here and talk. I know I could talk about rockets all day. But that's the important thing for the next generation to realize, is it is a teamwork thing. Spacecraft guys, when they build, scientists that get involved, it's huge. Space is cool. Space is really cool, and launching rockets is awesome.
Well, on that awesome note, we're going to thank you very much for joining us today.
Thank you guys.
All right, our last speaker this morning is Joe Pica, who comes from the National Weather Service, to talk a little bit about how they're going to end up using some of this data. So, Joe?
Thank you. I'm really excited to be here today representing NOAA's National Weather Service for the launch of the GOES S satellite. For the Weather Service, our primary mission is to issue weather forecasts, watches, warnings to protect lives, property, and ensure the national economy. And a big part of this is weather models and observations, and particularly satellite observations. It's actually been a really good year and a half for us bringing new technology into space. So GOES R was the first of those that was launched, and it's now in operations as GOES East. In last November, we launched JPSS-1, which is now NOAA 20 on orbit, and it's going through its calibration and validation phase. But it's a polar orbiter instead of a GEO, and that really informs our weather models. And now, tomorrow we watch the launch of GOES S, and so we're really excited about that. GOES S is actually going to go up, and then we'll be bringing that in several months into operations as GOES West. And so the capabilities that we're realizing with GOES East with GOES 16, we'll realize those over the West as well. So the capabilities for monitoring forest fires, we have tropical cyclones in the Pacific as well, so we'll actually be able to watch those. Most of the weather starts over the Pacific and comes across the United States, so we'll be able to see it earlier. We'll be able to forecast weather for that maritime traffic that comes across the Pacific and delivers goods and products to the United States and then out. Fishermen that are out there, all those folks will benefit from these capabilities, and so we're really excited about this. What we found with GOES 16 is it's really a game-changing capability for us. It really is going from black and white still imagery to high-definition color video. It really is that kind of capability. Even more so with that temporal refresh, it really is getting to the time frames every few minutes that our other observing systems like our radars And our needs, such as tornado watches, you need minutes notice, not an image every 25 minutes. So it's really getting more in line with our requirements for being able to protect lives and property. So with that, let me show you an example of that from last year. If we could cue the video, please. So this is an example of one of the hurricanes last year. 30-second imagery from GO-16. It was still in checkout phase. So we didn't even wait until it was in operations. We actually had it all the way through to our forecasters, and they were able to use it. They had the primary there. But in this particular case, we're watching Hurricane Harvey, 30 seconds, and it's a capability where we can actually zoom into certain areas and refresh those even faster than the overall scan of the hemisphere. With that, we were able to see very detailed imagery. And the forecasters in Corpus Christi, in this particular example, they were watching this, they were watching their Doppler radar, and they were in contact with the emergency managers. The emergency managers got out and performed rescues while the eyewall was over. During the calm of the eyewall, they were able to perform approximately 200 rescues and then get back into shelter. That's tactical knowledge that they were getting from the forecasters there to save lives and property directly. So really incredible capability, and we look forward to this, being extended to the Pacific with GOES-S. So, I'll add, based on one of the questions that was there, there's 2 points that we really like, or that I liked for GOES-R, and that was just before the countdown ended, and we went go Atlas, go Centaur, and go GOES-R, and tomorrow it'll be GOES-S. So listen for that if you're listening to the countdown, because I think that's really important. And then my favorite time frame for what's really important for us is when we see that first image, going to our forecasters so that they can actually start to look at this and appreciate what it is. So that's still, it'll be a couple months down the road, but that's really exciting for us when we're seeing that in the checkout phase. And with that, I'll open up for questions.
All right, we'll start down front here, and then we'll go over to the side.
I've been using weather satellite imagery since it came across Alden fax machines on wet fax paper. So let me compliment you guys on a fantastic platform. You've really done a tremendous service to the country and to science with this thing. I think they all deserve a big hand.
Thank you.
One of the weaknesses of NOAA and National Weather Service is that they don't have a national lightning network in place. There are private enterprises that do that now. With the lightning mappers that is on the GOES-R and GOES-S, will the National Weather Service be offering a national lightning product similar to Nexrad and so forth?
So that's a great question. We actually are looking right now. We do purchase lightning, so we have lightning data on the ground from a couple of vendors, and then we're looking at how would we couple that with the geostationary lightning mapper to issue just exactly what you said, a common lightning product. We're actually, this is one of the more exciting parts of this satellite, where the GLM is a brand new instrument. So there's still a lot of things that we don't know yet on how we'll use it. We know that it actually is an indicator of severe weather, some of the most severe weather, and it's very important for us to have. But how do we incorporate it in models, for example, as opposed to just using for situational awareness to give us that sense of where the most severe weather is starting? So some of the things we're doing research into, and I think over the next few years we're going to see those incorporated, and that's a pretty exciting time for a lot of researchers at places like the University of Oklahoma and other places to fully utilize and exploit that data.
All right, next question is going to be over on the side here.
Obviously, the program's relatively young, and there hasn't been data for that long, but have there been any unusual or unexpected ways that you found to use the data in the last year since GOES-R has been operational?
Absolutely, in several areas, but let me give you a specific example. When we, just 4 days after we turned it on in the checkout phase, we noticed the spectral bands were showing hotspots over the panhandle of Texas and Oklahoma. We actually, the forecasters were able to call the emergency responders in the area, and that was actually their first notice that there were any fires in that area. So before any 911 calls. So the resolution and that refresh capability, temporal refresh, was better than we even expected for picking up some of those things. And then further, we're able to use it tactically every minute to say, hey, we're noticing a wind shift. And so the hot spots were starting to move. So that was one area where we're saying, wow, this really is a game changer in our capability. And now we've already got emergency managers doing tabletop exercises with us to say, well, how do we better utilize that? So thank you.
All right, the next question will be down front.
So I have a question. How is the GOES satellites being integrated with the information that's coming off of the Landsat program? Because it seems that there'd be a lot of mixed data that could be used together, but they're coming off of really different platforms. So I'm just curious how these two are going to be integrating.
Great question. So in an earlier presentation, Tim showed you a map of the entire constellation of satellites we use for weather, mapping of land surfaces, and we use land surface information in our models, base information models, and we try and incorporate these to the best that we can. And there's still a lot of work to be done, particularly with the geostationary, to do that. So, for example, on another tact for this, when we get GOES R and GOES S working in tandem as GOES East and West, there's going to be a stereoscopic kind of view over the continental United States that we've never had before. This can allow for better characterization of winds or of clouds at various levels, and we actually derive winds from those that we feed in our numerical weather prediction models. So one of the errors in the traditional GOES is the height specifications of those, and that's really critical to accurate weather models.
All right, time for our last question here.
We learned earlier that with GOES R, we could make the invisible visible, such as turbulence, which as someone who doesn't love to fly, I thank you for that. What other invisible things are becoming visible, are becoming possible because of GOES R and GOES S?
So I would say that it's not just that we're seeing certain things. We have been able to go back retroactively after a plane saw some turbulence and actually pick it up running through the imagery. But I think the temporal refresh is really what's showing us it was there, but if you're only seeing an image every 25 minutes, you really don't pick it up. But when you see it every minute, you're seeing a video and you're seeing weather as, like a living thing. The director of the Weather Service yesterday, he's from the University of Wisconsin, and he cited a professor there in the 70s who envisioned geostationary imagery to watch weather. And his quote was that the planet stands still, but the clouds move. And I mean, he must have been envisioning what if we could actually see the clouds move and what they're doing. And we see things like gravity waves or very small features in the weather that we never ever saw before. And so it's going to open up a lot of research areas on how are we going to improve our capabilities to improve lead times and protect lives and property. Thank you.
With that, we look forward to tuning in tomorrow for live launch coverage on NASA television. We'll also have live coverage across social channels from @NOAA and @NOAA Satellites and @NASA and @NASA Kennedy. And so we look forward to seeing all of you online. If you want to watch from home, you can watch it on the website at www.nasa.gov/live. We're looking forward to it. Launch window opens at 5:02 p.m. Eastern Time tomorrow. Go, GOES S.